everyone for coming. Today I'm going to talk about increasing your design and validation productivity using formal verification. So now so I'm going to start by defining what formal verification is, give you sort of a motivating demo, then just talk a little bit about how it compares to stuff you're used to and where it fits into your design flows. So I'll start by defining it. Right, so really the simplest definition I like to use is it's just a mathematical analysis of the space of possible behaviors of a design. All right, so what does this mean? Well, again, you should think of formal verification as sort of a family of applications, not just one tool, right? It's referring to, in general, when you're mathematically analyzing what your RTL is going to do rather than just trying specific values, right? So doing sort of this kind of mathematical analysis is, of course, the way engineering should be done, right? Anything you're designing, you want to figure out, you want to write the equations and prove that's actually going to do what you want for all possible cases. You don't just want to try specific values, right? If you're verifying your chips just with simulation, it's kind of like, you build a bridge, keep sending trucks over it and see which trucks make it fall, right? You don't really know if all trucks will be able to cross the bridge, right? Unless you do the math, right? And that's what formal verification lets you do. Right. And since it works on the behavior space of your design, you can analyze all sorts of interesting things. Like in simulation, of course, you have to drive the inputs and see what happens. But in formal verification, you can look at the inputs, the outputs, or even internal states and try to compute what it takes to get there. Right. And in the demo, you'll see more clearly what that means. Right. So the philosophy I always like to drive towards is use formal wherever you can and only simulate where you must. So let's look at this more concretely. What does this mean in real life? So here's an example problem you have. If you've done any level of designing, I'm sure you've faced this. And in a past life, I did some design engineering. And it always frustrated me that when I create an RTL model, there's nothing you can do with it, right? You have to wait for the validation guys to create a test bench, or else write a little dinky homemade test bench that just tries a few things. But it's really hard with only simulation to just see what your RTL model is going to do and understand if it's working correctly, and for the majority of cases once you've written it, right? But what we'd really like to do is as soon as we write our RTL, we want to be able to examine behaviors and ask questions about it and figure out if it's doing what we want. So here's an example. We've written some little design that has a state machine, and we have this variable parse state that indicates what state we're in. And we want to ask the question, can we reach the checksum state with some set of inputs, right? A basic question you might ask about something you've just written, where you want to figure out, okay, have I, coded my state machine in a sensible way so I can get through all the states? Well, rather than having to think independently about what inputs it takes to get there, what you can do in a formal verification tool like Jasper is you right-click on your state variable, right, and say you want to visualize a situation where this state variable reaches this checksum state. And we're not telling the tool anything about what inputs to drive. The tool is going to compute backwards from that request and figure out what inputs it takes to get us to this checksum state. So what's going to happen is it'll come out with a waveform that it's automatically generated, right? So I didn't have to tell it the inputs to any of these signals cycle by cycle. All I did was tell it what the clocks and resets are for the model, and it figured out a way to get into that checksum state, right? In this case, it requires this series of values that you see in this waveform, right? And this set of values will get you into that state. So now we can see an example of real behavior on our design. And you can think if you were writing a little homemade test bench, you would have had to set values for all these signals at each cycle. It would have been a lot of work. But here, with just one simple request from a formal verification tool, we can get a waveform up that goes through this, non-trivial four-state example to get us into that checksum state. Now, another cool thing we can do is, we can look at this and ask further questions of the waveform. Again, that's something you can never think of doing in a simulation tool. But let's suppose we look at this and we notice that, okay, well, we got this example, which is great, but we know that we designed the state machine to handle multi-cycle headers, right? So headers don't have to be always exactly one cycle. Maybe we're nervous about how we designed that, so we want to ask the question, okay, can we still meet our requirement of getting to the checksum state if we allow a packet with a 5-cycle header? Well, again, we can just click on the screen and ask that question. We tell it, okay, we want to see that the state equals header for 5 cycles at some point during this waveform, while still, of course, meeting our initial condition of reaching the checksum state. So We put this new condition on the waveform, and again, the tool sort of solves by computing over the space of possible behaviors. And now it comes back with a waveform that meets our new requirement, right? So we still reach that checksum state like we did before, but now we do it in a situation when we had a 5-cycle header, right? So again, we're able to sort of ask more questions about what's possible in this design. And now, of course, we'd written a homemade test. It would have been more complicated to get here. Yeah, we would have to account for 7 cycles worth of driving inputs, but now we don't have to because the formal verification tool solved all that for us. We can continue asking further questions. Like one question that you often ask when you're debugging waveforms is, is there a simpler way to do this, right? So we might notice that, okay, we met all the requirements we gave so far, but we noticed that the data is changing every cycle. Is it really expected that your data has to change every cycle during a 5-cycle header in order to progress the transaction? Well, you can ask that question and tell the tool, okay, yeah, this example is great, but I want a simpler one, right? And in the Jasper tool, of course, we call that requesting a quiet trace. And what the tool does is it thinks for a little while, again, looking at the space of possible behaviors, and it'll come back a little later and say, okay, here's a quiet trace for it. So now you can see it came up with an example that has a lot fewer transitions in it. Right? And of course, this is extremely useful when you're debugging, messy errors, right? Because you want to say, okay, what's a simpler way that this can happen, right? So you're not distracted looking at transitions that didn't really matter for the error that you care about. And again, this is a thing you could never dream of doing in a simulation tool, right? You'd have to write a whole different test to see if there's a quieter example for this. But with the power of formal verification, all you're doing is adding an effective assumption, right, or request to keep this the signals from transitioning as much, and the tool can solve for that. So now that we've seen a demo of the cool things you can do with formal, let's take a step back and compare how formal verification works versus simulation. Now, really, when you're doing any kind of validation process, you want to really think about, one of your goals is to cover the state space, right? So by the state space, I mean, you look at the values of all the inputs, flops, latches, et cetera, in your design. Of course, this is an exponential size space, but it is finite, right? There's only a finite amount of stuff your design can do. And you can think of design validation as ensuring only good states are in the state space, right? So if you're only able to reach things that are what you expect, then that's good, right? So if you have like an adder and you can reach the case where the sum is wrong, that's bad, right? You want all the states you reach to be the cases where your adder gives the correct answer. And that's, you can think of validation as doing that, analyzing your state space and figuring out, can you reach any bad states, or can you prove you reach only good states? Now in simulation, you're trying to figure this out just by analyzing one path at a time, right? So you can think of yourself as following these red lines along here. And, if you reach a bad state, you found an error. If you reach only good states, that's great. But the key thing is simulation is only checking this, one possibility through the space at a time, which of course in an exponential space means that you're only doing a very small sampling of what can happen in your design. Now, formal verification, because it's doing a mathematical analysis of the behavior space, really is analyzing the whole space. And you can use formal verification not just to hunt for bugs, but to also prove the absence of bugs, a very powerful thing. Now, of course, this middle picture is kind of the ideal state. One disadvantage of formal is, of course, because it is doing something so much more ambitious than simulation, right? Fully analyzing an exponential space, then its capacity isn't as much. So you can't just take your full chip model and plug it into formal verification. So you have to sort of break down the problem, put smaller parts of your model or parts with restricted behavior in the formal verification tool. So you end up with something more like this third picture here, where you have some regions of the space that you've fully explored using formal verification. You probably, in any realistic design, you can't explore the entire space with formal verification. So you will have some bug hunting you still have to do with simulation, emulation, those kinds of things. But for significant portions of your design, you will be able to run formal verification and with high confidence prove the absence of bugs, and validate with exponentially higher coverage than you get out of simulation methods. So let's look at a few details of simulation versus formal in practice, right? So one issue is the values checked, right? In simulation, of course, you're checking specific test values. You're describing the journey, right? You're describing how you get to any state that you want to get to. And you can try to limit the values driven to be more realistic, but you're really sort of just trying to describe the journey step by step with any sort of simulation test bench framework. While formal, again, is analyzing the universe of possible values. So you're describing the destination rather than the journey, which is a much more powerful thing to be able to do, right? Because the tool can solve backwards and figure out, okay, can you get to this bad state? Can you always get to these good states, etc.? Then when you're debugging, formal is also a bit different from simulation. At first people say, oh, well, both of them you debug waveforms, so that's the same, right? But actually, the waveform debug you get in formal verification is much more powerful. Right? Because in simulation, you're really working with a fixed waveform at any time, right? You see the waveform generated by your test, but for any changes to that, you really have to modify or rerun the test, right? You can't do the things like I just did in the demo, or you look at the waveform, say, oh, well, that gives a 1-cycle header. Let me see a 5-cycle header, right? The only way to do that in simulation is to really modify your test and rerun it from the beginning. Well, again, in formal verification, you have sort of a modifiable waveform. You can add live constraints and replot. Again, because it's solving over the behavior space, you can say, I want something different to happen in the middle or at the end. Whatever you want to do, you just specify your destination and the tool figures out the journey. Right. And then, of course, the tool can do things like I showed you with quiet trace, where you say, okay, well, you've met all the requirements I want, but I want fewer transitions, or try to make the example simpler. And formal can do that. Well, of course, you couldn't dream of doing something like that in simulation. So then there's a question of validation efficiency. Right. And, a lot of people are used to simulation, and they think, oh, well, simulation's efficient just because any individual test you can run quickly in simulation. But the thing is, finding any bug depends on specific tests, right? So you can run lots of simulations, but you're still just exploring these linear paths through the space, like I showed you. You're not really doing any kind of comprehensive coverage. While in formal verification, each run is covering the full space of behaviors, right? And so it's common to find corner case bugs, right? So misbehaviors you never would have thought of, that are really sneaky and can be really difficult to discover, right? So it's especially important these days with things like security, where it's that sort of rare corner case that matters. Even if in normal cases where people do what you expect, it works great, but that one very weird case where someone put in some tricky hack, things like that you would discover with formal verification, but not with simulation. But of course, there are some disadvantages to formal. Of course, the big one is capacity, like I mentioned, because formal is tackling a much harder problem. It has a lower capacity than simulation, right? A simulation, you can run it, a full chip model, right? And that only has linear cost essentially in the model size. Right? Well, formal verification, because it has the worst case exponential performance, you have to be running at a slightly lower level typically, or make some compromises. And then similarly, in terms of design styles, simulation can handle, well, fully general system Verilog for the most part, while formal verification has some limitations. It can only handle synthesizable logic, and there are certain families of designs, in particular complex data transformations, that can be really hard to test with formal verification in a lot of cases. All right, so let's look at where formal fits into your design flows. Now, one thing you should think about is the fact that formal verification is really a toolkit, right? So it's a general methodology for mathematically analyzing your design, right, provided by core tools like Jasper from Cadence. But we build on top of that many different apps, right, many different specific things you can do with it in your flow to help verify your design, right? So formal property verification, where you're just verifying properties on your RTL or on your architecture, is the thing most people think of first as far as formal verification goes. Right? You write an assertion, you want to verify that assertion is always going to be true. And of course, this is very powerful. And you also want to think about, though, using this FPV early, right? What I just showed you in the demo is what I call design exercise, where rather than trying to do validate for rare corner case bugs near the end, you're starting at the beginning, right? And when you first write your RTL, just trying to figure out, okay, do all the behaviors make sense? And actually, once you're used to using formal verification, doing this sort of early testing is actually a much easier way to test new RTL than writing little homemade simulation test benches, I think. There's other common apps, right? Sequential equivalence checking, where you verify two models are equivalent. And the cool thing with sequential equivalence checking, as opposed to maybe the LEC that you might be familiar with for comparing RTL to netlist for synthesis results, is that sequential equivalence checking doesn't require state matching models. So you could write, if you're doing an ECO or an engineering change that, for example, recodes a state machine, you can use sequential equivalence checking to make sure that the behavior is going to be the same in all cases. Then we have apps like SuperLint, where you're probably familiar with linting, where you do sort of initial RTL checks, and by adding the power of formal verification to those, you can actually do some more powerful checks that aren't available in simple syntax-based lint tools. There's connectivity verification, where you try to prove your top-level connectivity map is correctly implemented on an SoC design. It's a problem that can be very messy to solve with simulation, but very easy to solve with formal. As you can see in the picture on the right here, we have a whole bunch of Jasper apps I haven't gotten into. There's just a lot of different ways you can use formal to enhance your design and validation. Right? If you want to look at where things fit into the design flow, we can see that in your early stages, where you're doing architecture and RTL modeling, you have a bunch of things you can do. You can do FPV, formal property verification, at these levels. You can also use design exercise, like I showed you in the demo, to check early RTL. It's things like the SuperLint and clock domain crossing. And you can also compare C models to RTL, another really growing area that's very powerful for verifying arithmetic operations in your designs. And of course, the traditional validation stage, where people most often think about FPV, and some related things you can check, like XProp to check for X's. You can also check for design coverage, things like that. Then even in the back end, formal is still useful, right? Especially if you implement late ECOs, right? So a lot of times when you're getting close to tape out, you'll suddenly find a bug you have to fix. You want to make sure that your design is still equivalent to what it was before, right? Sequential equivalence checking can be very important there. And even in post-silicon, actually, a lot of people don't think of formal for post-silicon, but actually in post-silicon, a lot of times the issue you hit is you see something happening in the lab, right, that doesn't happen or didn't happen in any of your simulations, right? So inherently, that means that there was some behavior possible that the simulation tests you wrote just weren't able to cover. And of course, because formal verification solves backwards, right, you can specify the destination, not the journey. It's a perfect tool for taking a bug you cited in the lab, plugging it in and trying to ask for, okay, show me how I can get to that bug in the RTL model. Right? And I've known some post-silicon engineers who insist on having FPV licenses available as an absolute condition for embarking on any post-silicon effort, because in these situations, this method is just critical. So, okay, so yeah, so as far as the summary, let me just quickly go through some challenges that you hit when you're doing formal verification. Right. And one of them is that formal verification is really a change in your mindset, right? So in simulation, you're sort of actively driving tests. Well, in formal, you're trying to look at target behaviors when you constrain them passively through writing assumptions that limit what your model is allowed to do. There's also the FUD, right? The fear, uncertainty, doubt factor that scares a lot of people, right? They worry about the fact that formal is exponential in the worst case, right? So does that mean that we might get stuck if I try it on my design? Also a question of coverage, right? People are used to measuring coverage in simulation. How can they be sure about their coverage in formal? And a lot of people are just nervous about training issues or setup time. But actually, all these issues are things that are, I think, not really, insurmountable, right? Actually, these are just minor glitches, and once you're used to formal, you'll see that none of these are really major obstacles. Yes, formal is a change in mindset, but I think a lot of people would agree once they've gotten used to using formal, it's actually a lot easier to use than simulation in many ways as a strategy for testing your model. So once you're used to formal, I find simulation very painful to use, in comparison. When people worry about complexity, well, there's a whole bunch of techniques that are very widely known for dealing with complexity to sort of fall back to simpler methods that combine formal with maybe simulation, other technologies. So these days, if you choose appropriate targets for formal, it's extremely rare that you really get mired down in complexity issues to the point where you have to back off of formal. As far as coverage goes, pretty much all the major formal verification tools now offer coverage checking, and actually more precise coverage checking than simulation in a lot of cases. As far as training goes, of course, there's a lot of training available from various vendors, and of course, from Cadence, we can, if you have a team that's trying to ramp up on formal, we have lots of great training classes available. And of course, there's my book, which was mentioned before. And then as far as setup time, really, I think that setting up formal verification is actually much easier than setting up simulation. People say formal verification is hard to set up just because they have some simulation team that's probably 10 people who've been working for, a decade on setting up really elaborate simulation environments for your design. And people come in with the new formal from scratch and say, oh, this isn't as easy to use as that thing those other guys spent, 10 years putting together scripts for. But, if you compare apples to apples and look, okay, I'm embarking on a new effort, do I want to set up scripts to run formal or scripts to run simulation? You'll actually find that a lot of times it's much easier to write scripts to set up formal. So why use formal verification, right? So these are sort of the key methods or the key reasons you should take away from this. Right? First of all, it's a systematic method, right? It mathematically analyzes the problem space, right? It's not dependent on, choosing random values and trying them, things like that. So it's really fundamentally the right way to do engineering, right? Formal generally gives you solid validation for a lot less effort, right? Once you're used to formal, you find the ROI of verifying a design using formal is really good, right? By targeting behaviors rather than inputs and being able to solve backwards from your targeted behaviors, it's actually much easier to sort of hit corner case bugs as well as to just, complete your validation goals in general. So overall, with formal, you can improve your productivity and your schedule. You can shift left to catch bugs sooner. You can replace a lot of unit level testing with formal verification. And as we saw, we have a lot of apps to target specific problems across the design flow. So the philosophy is, as I mentioned, use formal wherever we can and only simulate where we must. Now, if you want to bring formal verification to your company, that's great. We always recommend the crawl, walk, run model, right? Where first you crawl, right? So you start by developing a single expert in formal. Maybe you, if you chose to come to this talk, you're probably interested enough, right? So learn the basics of formal, start using formal on some individual design that you own, right? Or one piece of RTL from your project, right? And then once you've convinced yourself that it's working for your design, that you understand the basics, then you commit to using it in the longer term. So once you've decided you want to use it in the longer term, then you really want to look for cases where you can demonstrate real value, right? So if you're in any real life chip design project, there are probably current problems that are really bugging the validation owners, right? Maybe we're escapes on past designs in some complicated area, or there's some block that gets low coverage in simulation. It's just really hard to write simulation tests that properly target all its behaviors. Or maybe there's a known weak area in your validation, like connectivity or clock domain crossing, right? So you want to look for a problem that you can have, that you can solve with formal and try to demonstrate a clear win on it. And of course, your first problem you try on may or may not work, right? You may have to try a few things to see what gives the best ROI for your particular company and your particular projects. But chances are, again, you'll probably find something where simulation just isn't fitting the bill, and where formal is much more productive. Then once you've demonstrated the power of formal, then you really want to try to gain buy-in from your whole team, right? So, from your fellow individual contributors, tell them how much more easier to use and fun it is to do formal rather than simulation. Of course, tell your team leads how this will accelerate project goals, and try to demonstrate return on investment. So show how much time you spend on formal versus the number and quality of bugs you find, and you'll probably find formal comes out really well there.